Hello, today we're going to talk about 11.3 asymptotes and discontinuities. Okay, so in regards to rational expressions, because a rational number means it can be written as a fraction, we have denominator, and denominators can never ever equal 0. So because of that, we end up with asymptotes. So today we're going to talk about when we have vertical asymptotes and when we have horizontal. But let's start with first example here, and it asks us the question: graph the line y equals x minus 2, and is it continuous? Is it continuous? So first let's graph. So if we want to graph, we need to plug in some easy points. Some easy points to plug in would be from -2 to 2. So if we plug in -2, -2 minus 2 is -4. -2, -4. -1 minus 2 is -3. 0 minus 2 is -2. 1 minus 2 is -1. And 2 minus 2 is 0. So because this is linear, your highest degree is x to the first. We can connect all of these points to have the line include every itty bitty decimal in between. So if we are graphing a line, which is what that y equals x minus 2 represents, is it continuous? So do I have any breaks, gaps, holes? No, I don't have any breaks, so therefore yes, it is continuous. So no breaks, holes, or gaps of any kind. So let's look at the second one. And now we have the rational expression y equals x minus 2 times x plus 3 divided by x plus 3. Is this continuous? Well, what do we notice here? We have a rational expression. We have a fraction. And what do we notice? We have on the numerator x plus 3, and on the denominator we have x plus 3. Well, anything divided by itself is just 1, so those cancel. So we're left with y equals x minus 2. Well, what do we notice there? Is that not just the graph of the line that we graphed on this left-hand side? It is. If I were to plug in these values, x and y values, I would get almost the exact same thing. So let's take a look and see, but we're going to extend our graph all the way down to -3 this time. But let's see what happens when we plug in -3 into the original equation. Well, if we plug in -3 into the original, I'm going to be dividing by -3 plus 3 is 0. So I'm going to be dividing by 0. I can't divide by 0. That is undefined. So actually, I end up with a hole at -3. I end up with a hole at -3. Now if I plug in -2 again, -2 minus 2 is -4. Again, those would cancel. I'd still end up with -4 here. Let's see if I can get that point. There we go. -1, I'd still get -3. At 0, I'd still get -2. And at 1, I'd still get -1. So notice, because my x plus 3's cancel, because one's on top, one's on bottom, they divide out by 1, it is still a line because the remaining function is a line, y equals x minus 2. But I have a restricted value. My restricted value is -3 because that is the point at which my numerator and denominator cancel. So what we end up having is, if you have a rational expression and you are able to cancel out a term because the numerator will divide out by the denominators, we're going to have what's called a hole. You're going to have a hole at x equals -3, i.e. x cannot equal -3. So holes occur anytime something cancels. So with rational functions, reading what's down here, is a function whose numerator and denominator, they are polynomials. The most important difference between graphs of rational functions and the graph of polynomials is the presence of discontinuities, such as holes or asymptotes. A hole is a point where a function is undefined, so just one single value. An asymptote is an entire line that the graph squeezes up against, gets really, really close to. It might actually touch it oftentimes. It doesn't, but there are times that means it approaches, it gets really, really close to. So let's find the hole on this first rational expression. So we have f of x equals x squared minus 4 divided by x plus 2. Well, let's take a look at that numerator here, and we can factor. Well, 4 is a special kind of number, so this is a difference of square. Square root of 4 is 2, so this would be x plus 2, x minus 2. And our denominator is x plus 2. Well, what do we notice? On top and bottom, I have a common factor of x plus 2 divided by x plus 2. That's going to cancel. And so I'm going to be simply left with x minus 2. So what's going to happen is that the resulting graph is going to be a line of y equals x minus 2, because x to the first power graph would be a line. But because I canceled a value, I'm going to have a hole at the value of that canceling where it equals 0. So if I cancel out x plus 2, that means that I have a hole at x plus 2 cannot equal 0, therefore x is not going to equal negative 2. So I'm going to have a hole at negative 2. So let's plug in negative 2 and see what actual value we get. If I plug in negative 2 minus 2 is negative 4. If I plug in negative 1 minus 2 is negative 3. Again, that's going to hit exactly. If I plug in 0 minus 2 is negative 2, and so forth. So the graph of this rational will actually be a line, what appears to be a line, with a hole, a missing value, at x equals negative 2. So first kind of discontinuity is a hole, a one point that is missing from the graph. Another part of discontinuity could be what's called a jump. So here we have what's called a piecewise function. It's a function that is in pieces. So how do we graph a piecewise function is we have to follow the notation. So let's look at the top part, x plus 1, where x is greater than or equal to 1. So first, because it could equal 1, let's plug it in. 1 plus 1 is 2. So when I plug in 1, I get the value of 2. And this restriction tells me when x is greater than 1, I'm going to be plugging into the top equation. So let's plug in 2. 2 is greater than 1. So 2 plus 1 is 3. Plug in 3. 3 plus 1 is 4. And because this is just x plus 1, if I keep going, I'm going to be continuing to go upward towards a line in the right-hand direction. Now let's look at the lower function. The lower function would be that when x is less than 1. Well, first let's plug in 1 so that we can figure out the starting point. Even though it won't actually equal 1, we can put an open dot there, showing that it's not going to hit exactly 1. So let's plug in 1 into the lower equation, piecewise equation, so that we find our starting point. So 2 times 1 is 2. 2 minus 3 is negative 1. So at positive 1, we're going to have a hole at negative 1. And then we just have we have a linear equation here, right? When x is less than 1, that means if I plug in 0, 0 is going to be negative 3. And so forth. So we're going to go down to the left. So there is our what's called a piecewise function. It's in different pieces, which means that we have a certain discontinuity called a jump. Okay, so notice we have a whole range of values that the graph is missing from. And the last discontinuity is an asymptote. Okay, remember an asymptote is an entire line that the graph is getting close to. Often never touches. Sometimes there are cases that it does cross it, but it means that it approaches, it gets really close to. So notice we have the rational function f of x equals 1 over x squared. So let's plug in some numbers to figure out what are some possible values on my graph. And some easy numbers to plug in. Let's start with 0. Can we plug in 0? What happens at 0? 1 divided by 0 squared is just, it's not even 0, it is undefined. So I cannot plug in 0. I have an asymptote at 0. I have an asymptote at 0. Well, what happens when I plug in 1? 1 divided by 1 squared is just 1. So 1, 1. 2, 1 divided by 2 squared is 1 over 4. So we're getting very close to that x-axis. If we plug in 3, 1 over 3 squared, 1 over 9. So notice we're getting closer to what happens. If I plug in a very large number, 10, 1 over 10 squared is going to be 1 over 100. That's just getting even closer. So actually, we have two asymptotes here. This is going to get closer to the x-axis, but it's never ever actually going to cross it. So rational functions can look very tricky. This is going to get closer, never actually going to cross it. Well, let's see what happens on if I plug in the negative side. Okay, if I plug in negative 1, well, negative 1 squared is 1, so 1 divided by 1 is 1. Let's plug in negative 2. So negative 2 squared is 4. 1 over 4 is 0.25. And we can continue down the graph. So there is the graph of the rational equation f of x equals 1 over x squared. So two asymptotes there. You have a vertical asymptote, up and down vertical asymptote at x equals 0. And we have a horizontal asymptote at y equals 0. Okay, so next let's practice finding those discontinuities as well. So determine the place of discontinuity for the function. So remember with discontinuities we have either a hole, a jump, or an asymptote. Well, a hole happens when we are canceling anything. So let's look at our rational expression, 1 divided by x minus 4. Notice we don't have any quadratics at all, so we're not going to be canceling, so we don't have a hole. Do we have a piecewise function? Do we have different pieces of the graph put together? Nope, which means we're going to be having an asymptote. So asymptotes happen when the denominator cannot equal 0. So let's look at that denominator, and what do we notice here? X minus 4, because it's in the denominator, can never, ever equal 0. So what x value is going to make that go to 0? If we add 4, x cannot equal positive 4. So we are going to have an asymptote, imaginary line that the graph is never ever going to cross, at x equals 4. So let's look at the second one. We have the irrational expression x squared minus 1 divided by x squared plus 3x plus 2. Well, first step, anytime we have a quadratic, is let's see if we can break that down into its linear components. Okay, let's try to break it down into linear components. So here, notice the top one, we have two terms. So we're looking for a parenthesis. And since we don't have a middle term, 1 is a special kind of number. So this is a difference of squares. So the square root of 1 is 1. So we have x plus 1. X minus 1. And let's look at the bottom. We're looking for two numbers that multiply to 2 but add to 3. So two numbers that multiply to 2 but add to 3. 2 is prime. You only have 2 and 1. So this would be x plus 2 and x plus 1. So what do we notice here? If we look at my rational expression modified, what do we have on top and bottom? We have an x plus 1 on top. We have an x plus 1 on bottom, so those cancel. So Simplified, we end up with x minus 1 divided by x plus 2. So because we canceled the x plus 1, we are going to have a whole at positive 1 because right here x plus 1 cannot equal 0, so x cannot equal negative 1. So we do have a whole at x equal negative 1. But notice what also is remaining. I still have a denominator. So if we look right here, our denominator cannot equal 0. Therefore, we also have an asymptote. So our denominator cannot equal 0, so x plus 2 cannot equal 0, so x cannot equal negative 2. So we also have an asymptote at negative 2. Vertical asymptote at negative 2. So let's look at the last one. Graph the function x squared minus 1 divided by x minus 1. So first, let's see if we can factor the top. So here we have, again, a difference of squares. So since this is 1, this is x plus 1, this is x minus 1. So what do we notice? What's going to cancel on top and bottom? That's going to be x minus 1. And we're left with x plus 1. So if we think about this graphically, because we have something canceling, that means that we're going to have a hole there. So we have a hole at where it cancels, so x minus 1 means the hole is going to be at positive 1. So if I plug in 1 here, 1 plus 1 is going to be 2. So at positive 1, 2, we have a hole. So next, let's plug in values. So if you plug in 2, 2 plus 1 is 3. If we plug in 3, we're going to get 4. So we go continue up here on the right-hand side, continue down on the left-hand side. And there's the graph. Again, it's going to look like a line because it simplifies down to a line, x plus 1. But because we had part of it cancel, we're going to have a hole at that part where it cancels. Okay, so to help you graph rational functions, we have some 4 different key parts that we need to find in order to help us. If you notice on the right-hand side, these rational equations all look very, very different from each other. Notice sometimes we have linear, sometimes we have quadratic on top and bottom. So finding these 4 attributes will help us figure out what the shape of the graph will be. So let's first start off with a vertical asymptote. So what is a vertical asymptote? A vertical asymptote happens when we have an imaginary line vertically that the graph is never ever going to cross. So vertical asymptotes look like this. They're imaginary lines. Because they are vertical, they are x equal equations, always x equal. Well, how do I find them from my equation? I find them by setting the denominator equal to 0 and solving for x. Well, that's not too bad. So let's look at the equation, y equals x divided by x squared plus 4. And all we need to do is we need to take the denominator. So denominator here, x squared plus 4. Cannot equal 0. So if we add 4 to both, actually let's change this to a minus. To make this problem easier for us, we're going to make this a minus. My bad. Let's make that a minus. That will make it easier for us. There we go. So add 4 to both sides. X squared equals positive 4. And if we square root both sides, x equals square root of 4, which is plus or minus 2. So therefore, we have two asymptotes at plus and minus negative 2. So that, again, is a vertical asymptote at x equals plus or minus 2. Okay, let's look at the next one. How do we find a horizontal asymptote? Well, let's first look at a graph. What is the picture? A horizontal asymptote is a horizontal line, imaginary line that the graph gets close, close, close to, but is never ever going to cross. So because it is a horizontal asymptote, it is always a y-equal equation. It is always y-equal. And how we determine where a horizontal asymptote is we look at the degree. Okay, if the degree of the numerator is less than the degree of the denominator, so if I have x to the first over x squared, then automatically your horizontal asymptote is going to be 0. So if it's less than, it's going to equal 0. If your numerator is greater than your denominator, there will be no horizontal asymptote. There will be none. And if the powers are equal, if they're equal, then you have to take the coefficient of the numerator's highest divided by a coefficient of the denominator's highest power. And there is an acronym that will help you with horizontal asymptotes, and that is Bobo-Button. Okay, so what does Bobo-Button stand for? Big on bottom is 0. So if your degree is bigger on bottom, it's 0. Big on top is none. So if the numerator degree is greater, we have no. So let's look at our 3 examples over here, and let's see if we can determine what horizontal asymptote, if there is a horizontal asymptote anywhere. So let's look at the first one. Y equals x divided by x squared plus 4. So all we're looking at is the degree. So if we look at the degree, is it big on bottom or is it big on top? So if we circle this front one, so x divided by x squared, again, this is big on bottom. So this is big on bottom. So this is bigger on bottom because we have x over x squared, right? So because it's bigger on bottom, it's automatically 0. So it's going to be a horizontal asymptote at y equals 0. So let's look at the second equation, y equals x squared minus 2 divided by x plus 2. Again, all we're looking at is the degree. So we're looking at x squared divided by x squared. This time it is big on top. So we're looking at x squared over x. So because it's bigger on top, big on top is no asymptote. So there is no horizontal asymptote for this one. So let's look at the bottom one. What do we notice about the bottom one? If we look at the degree, we have squared divided by squared. So because they are the same, because they are the same, let me see if I can get that. I don't know why that's not writing. Let me fix that. So because it is the same, x squared over x squared over x squared, we need to look at the coefficients. So this is 1x squared divided by 1x squared. Therefore, my horizontal asymptote is simply y equals 1. Okay, again, why is it 1? Because if we look at our coefficients here, we have not a number there, which is an implied 1 divided by 1, which is 1. So next, how do we find the x-intercepts, or the zeros? Sometimes could often be called the roots. Well, the x-intercept, just like it sounds, is when the graph crosses the x-axis. Okay, so anytime you have a graph crossing the x-axis. In regards to the x-intercept, it's always going to be a comma 0. So how do we find the x-intercept? All we need to do is look at the numerator. All you got to do is look at the numerator. So set the numerator equal to 0 and solve. So if our rational equation is y equal x plus 2 divided by x minus 4, we just take a look at that numerator. X plus 2 equals 0, so x would equal negative 2. Therefore, our x-intercept would be at the value, at the point negative 2 comma 0. And finally, the y-intercept. Well, the y-intercept, just as it sounds, is when the graph is going to cross the y-axis. It's going to be this point. And it is always going to be a 0b type of point. Now, where do we look to find the y-intercept? You simply need to let x equal 0 and solve for y. So let's do that. So if we have the rational expression y equals x plus 2 divided by x minus 4, we're going to simply plug in x equals 0. So this is going to be 0 plus 2 divided by 0 minus 4. 0 plus 2 is 2. 0 minus 4 is negative 4. So 2 divided by negative 4 is negative 2. So actually, nope, I did that math wrong. My bad. 2 divided by negative 4 is negative a half. My bad, negative a half. So our y-intercept here would be the point 0 comma negative a half. Okay, so 4 key attributes that will help you graph a rational expression. Vertical expressions, x equal equations, look at denominator equal to 0. Horizontal asymptotes or y equal equations, look at the degree. Remember Bobo button. If the degree is bigger on bottom, it's 0. If the degree is bigger on top, it is none. And if they are the same, you have to go with the coefficients. The x-intercepts, you're going to set the numerator equal to 0, and the y-intercept, you're simply going to plug in 0. So let's put these into practice. How are we going to graph without a calculator the rational expression y equals x minus 4 divided by x plus 2? Okay, so we can find our key attributes. Domain, we're not going to be able to find until later. So let's start with the vertical asymptote. So I'm going to come over here on the side. Where do we look to find our vertical asymptote? Well, our vertical asymptote is by setting the denominator equal to 0. So this would be denominator equal to 0. Well, what is the denominator? The denominator is x plus 2. So x plus 2 cannot equal 0. Therefore, x cannot equal negative 2. So my vertical asymptote is at x equal negative 2. So I come over here on my graph, and at negative 2, we have that imaginary line. So now let's look at the horizontal asymptote. The horizontal asymptote, you look at the degree. So what do we notice about the degree? I have a x to the first divided by x to the first. That means we have the same degree. So the degree is the same as we have. So because the degree is the same, we look at the coefficients. So this is an applied 1, so our horizontal asymptote is at y equals 1. So y equals 1. So that is the horizontal line that the graph is never ever going to cross. Okay, so let's find zeros. If we look at zeros, where do we look to find zeros? zeros is by setting the numerator equal to 0. So 0 is the numerator equal to 0. Numerator equal to 0. So this would be 0 equals x minus 4, so x equals positive 4. So way over here at positive 4, I have a point that crosses the x-axis. So 0 is x equal 4. Actually, we should write it like this, 4, 0. And lastly, Y-intercept. So how do we find the Y-intercept? To find the Y-intercept, you simply let x go to 0. So we let x equal 0. So if we let x equal 0, that means y equals 0 minus 4 over 0 plus 2. So if we simplify, we're going to end up with negative 4 over 2. So negative 4 divided by 2 is negative 2. So our y-intercept would be at 0, comma, negative 2. And because we have asymptotes, that means the graph is going to come closer to this asymptote. It needs to intersect this x-axis and continue. So I have this shape of the graph, but rational functions always have symmetry. So what's going on this left-hand side? Let's just plug in an easy point, okay? Because we need this left-hand side of the asymptote intersection. Easy point that we could plug in, let's plug in negative 3. So if we plug in negative 3, so we'll come over here, plug in negative 3. Let x equal negative 3. So if we plug in negative 3, that means that we have negative 3 minus 4 divided by negative 3 plus 2. So negative 3 minus 4 is negative 7. Negative 3 plus 2 is negative 1. So negative divided by negative is positive. So this would be a positive 7. So at negative 3, we have way up here. So our graph is going to extend towards the asymptotes in that direction and come back towards this asymptote. So there's the graph of this rational expression, y equals x minus 4 divided by x plus 2. So again, every graph looks very different, okay? But if you find those key attributes, it makes it much easier. Oh, so we still haven't finished this off. Domain. What is our domain going to be? Well, domain is everything except your vertical asymptotes, okay? So because we have a vertical asymptote at negative 2, we have negative infinity to negative 2 union with negative 2 to infinity. And that completes our how to graph and find key attributes of our first rational.